This is your presenter Asloop Mudassar, and I am presenting slide number 73 of the course on laser physics. Question is, discuss level occupation at a thermal equilibrium in a quantum well semiconductor. Also discuss the physics of stimulated transition and related selection rules for quantum well semiconductor. The answer is, consider a quantum well semiconductor in thermal equilibrium. Let E prime represents the energy of a state either in conduction or valence subband. You see that here I am using the word subband. These are the bands which are formed in the quantum well of the two main bands, that is the quantum well in the conduction band and the quantum well in the valence band. And we have shown these sub bands labeled with n is equal to 1 and n is equal to 2, both for the conduction band and for the valence band in slide number 72. For the detail you may consult slide number 72. So here we are representing that E prime represents the energy of a state either in the conduction band, conduction subband, or the valence subband. The probability of occupation of this state is determined by Fermi-Dirac statistics. Let EF prime represents the Fermi energy. Assume that some electrons from the valence band are raised to the conduction band, more accurately to the subbands of the conduction band, that is n is equal to 1 band subband or n is equal to 2 subband. Also assume that there is a rapid relaxation among the sub-levels of the conduction band. So you see that here we are assuming that there will be a rapid relaxation among the sub-levels of the conduction band, and also there would be rapid relaxation among the sub-levels of the valence band. So also assume that there is a rapid relaxation among the sub-levels of the conduction band. That is from the levels for example the levels around n is equal to 2 to the levels in n is equal to 1 will be carried out through rapid relaxation in either the conduction band or in the valence band. So if n is equal to 1 and n is equal to 2 stands are the sub-levels in the conduction band, then the rapid relaxation will take place among these levels in the sub-bands of the conduction band. And similarly the same case is true for the valence band, that or more accurately for the sub-levels for the sub-bands in the valence band. Okay, if there is a transition to a sub-level of a valence band from a conduction band, then rapid relaxation is also assumed among the sub-levels of the valence band. The situation will introduce two quasi-Fermi levels, one in the conduction band and the other in the valence band. The probability of occupation of these levels is then given by the following equation. So for example, equation number 1, which gives the Fc of EC is equal to 1 over 1 plus e to the power EC minus EFC divided by KT. So this gives you the probability that in the conduction subband a level with energy EC is occupied. So let me repeat that this gives you, that is Fc as a function of EC gives you the probability that a sub-level with energy EC lying in the conduction band is occupied by the electron. And for the valence band we have Fv as a function of EV is equal to 1 over 1 plus e to the power EFV minus EV divided by KT. You see that we have changed the order of energies over here. In the conduction formula we have EC minus Fermi energy, and here we have Fermi energy in the valence band minus the energy of a level in the valence band, because you know that energy in the valence band are measured negative and the energies in the conduction band are measured upward, that is in the positive sense. But you see that here we are talking about in equation number 2 that EFV is what we are taking into account the magnitude of this energy without the negative sign, and similarly EV will be considered in magnitude without the sign. So FV of EV will give you the probability that in the valence band, that in the valence subband, an energy state EV will be occupied by a hole. Okay, the quasi-Fermi levels, you must remember one thing, that if the EC level in equation number 1 is lying below the FC level, then of course it will be occupied, and if similarly, and if the EV level is lying below the Fermi level in the valence band, then it will be occupied. So the general rule is that the levels which are below the Fermi level, they are occupied, and the levels which are above the Fermi levels, they are empty. So in the valence band, we are talking, if the levels are empty, it means that we are talking about the probability of probability that a hole with energy EV will exist. The quantum Fermi levels EFC and EFV are set by the density of injected electrons and holes into the relevant subbands. That is, the density of electrons will be injected into the conduction band, and the density for holes represented by NH will be injected into the valence band. For the case of quantum semiconductors, the densities are determined by, for example, equation number 3 gives you the density of electrons in the conduction band. So Ne is equal to integral of rho c over Lz. Here rho c is actually the surface density of state in the conduction band, and we divide it by Lz to give you the density of states in the density of states in the volume. That is the volume density. So rho c divided by Lz will give you the volume density of electrons in the volume density of states in the sub levels of the conduction band, and multiplied by the probability function, that is Fc of EC, I have explained it, and then multiplied by the DEC, because this is an integrand element. So this integral will give you, because you see that this is a general formula to find the number using the density of states and the probability of the occurrence of that states. So this Ne will give you, this Ne given by equation number 3 will give you the density of electrons in the sub levels of the conduction band. And then the formula NH, that is the density of holes, is similarly given by rho v over Lz, where rho v is the density of states, that is the surface density of states, divided by Lz will give you the volume density of state of the holes in the valence band, multiplied by the probability that a state EV will be occupied by a hole in the valence subband, and then of course integration is with respect to DEV. So this integral will give you the density of holes in the valence band. So equation number 3 gives you the density of electrons in the sub level of the conduction band, and NH will give you the density of hole in the sub level of the valence band, where rho with the subscript C comma V, that is this equation, can also hold for the conduction band and can also hold for the valence band. So that's why we have used the two subscripts together. So rho C comma V is equal to mCV divided by pi into h bar square. This rho has been addressed in slide number, in the previous slide, that is in the slide number 72. You can consult that slide in order to find this expression. So rho CV is equal to mCV divided by pi into h bar square. This is the surface density of states. The analytical solution of the integrals, that is the integrals given in equation number 3 and 4, gives. So these are the following expressions that we are giving without evaluating the integrals. So the density of states Ne is equal to Kt, summation over I, where I is summed over MCI over pi h bar square into Lz, and then into the log of 1 plus EFC minus EIC over Kt. And similarly, the density of holes is given by kT multiplied by the summation over I mvi over pi h bar square into Lz, and then multiplied by the log function log of 1 plus EFV minus EIV divided by kT. So these two densities, that is the solution of equation number 3 and 4, are respectively given in equation number 5 and 6, where MCI is the mass of electron in the ith conduction band, in the ith sub band of the conduction band, and MVI is the mass of the hole in the ith sub band of the valence band. Because V will stand for the valence band, C will stand for the conduction band, I stands for the ith sub bands, and M stands for the mass of the electron or the mass of the holes. For the conduction band we shall talk about the mass of the electron, and for the valence band we shall use the term mass of the holes, though they may be the same things. So EIC and EIV are the minimum energies in the ith sub-levels of the conduction band and the valence bands. Let us turn to the second part of the question. So you see that the second part of the question, what was that? That was discuss the physics of stimulated transition and related selection rules. So now we are going to discuss the stimulated transition. Probably we shall discuss first the stimulated absorption, which will be generalized also to the case of stimulated emission. So first of all we are going to discuss the stimulated emission, stimulated absorption transition and the relevant selected and the relevant selection rules. The interaction Hamiltonian when an electromagnetic wave of frequency nu interacts with the quantum well semiconductor can be written as H prime is the interaction Hamiltonian is given by the dot product between the electric dipole moment of the electron and the electric field of the incident beam, which is equal to minus ER dot with electric field E, where the electric field E is given by E is equal to E naught e to the power iota kW dot R perpendicular minus omega t. This is the incident plane wave at position R and time t, and omega is equal to 2 pi nu is the angular frequency of the light. For simplicity, E of R field is assumed to be polarized in the plane of the well. That is, E is polarized in the plane of the well, and the plane of the well is given by the coordinates x and y. R perpendicular is the component of vector R in the well plane. So R perpendicular, since this is the perpendicular to the Z, that is the quantum well width, so that why we are using it R perpendicular. E of R is constant in the Z direction, which is orthogonal to the well, as the wavelength of electric field E is much greater than the thickness of the well. So we can assume that the magnitude of E would stay the same over the thickness of the well. E of R is thus a function of transverse coordinate ER perpendicular. That is, E of R can be written more precisely as E of R perpendicular. Now consider stimulated transition, or more accurately stimulated absorption transition, which may occur from a sub-level in the valence band to a sub-level in the conduction band. You know that these sub-levels are associated with the quantum wells in the valence band and the conduction bands. For detail, you can consult previous slide, that is slide number 72. Let us designate energies corresponding to these states as E1 and E2. That is, E1 is a state in the sub-level of the valence band, and E2 is a state of the sub-levels in the conduction band. The transition rate W following equation number 36.12 is given by W is equal to pi by 2 into absolute square of H12 prime divided by H bar square multiplied by delta of delta omega, where nu naught is equal to E2 minus E1 over H is the transition frequency between the two sub-levels, that is between the level 1 and the level 2. So if you want to move an electron from a level 1 to level 2, you need to supply a frequency, transition frequency by the incident beam to be equal to nu naught, which is equal to E2 minus E1 over H. And H12 prime is given by integral of the wave function V. This is the complex conjugate of the wave function, block wave function, then multiplied by H prime. H prime is the interaction Hamiltonian we have just given above. For example, over here H prime has been given. So this is H prime Hamiltonian, interaction Hamiltonian, and then psi c, which is the block wave function of related with the subconduction bands, sublevels of the conduction band, and then integrated with respect to dV, where the block wave functions corresponding to sublevel 1 and 2 are respectively given by. We have also discussed this equation in much detail in one of the previous slides, especially given in slide number 36 and equation number 36.12. You can see the detail over there. And the block wave functions, that is psi v and psi c, have also been discussed over there. But now with respect to quantum well semiconductor, we are reproducing these wave functions below. That is psi c, that is the block wave function in the conduction band as a function of r is equal to uck as a function of r perpendicular multiplied by the phase term e to the power iota kc perpendicular dot with r perpendicular and multiplied by the sine of nc pi into z over lz, where nc is an integer. So just on the right hand side we have omitted the k with the special part of the wave function u, and we are just writing it uc rather than uck. So this is uc as a function of r perpendicular. The rest of the quantities are the same as discussed before. Now in equation number 10 we are giving the wave function, that is the block wave function corresponding to the valence band. So we have psi v as a function of r is equal to u vk as a function of r perpendicular, which is the special part of the wave function, multiplied by e to the power iota k v perpendicular dot product with r perpendicular, and then this phase term is multiplied by sine of nv into pi into z over lz, where nv is also an integer. And on the right hand side we have dropped the value, we have dropped the k subscript, and we have written only just u v as a function of r perpendicular, and the rest of the quantities on the right hand side in equation number 10 are the same as on the left hand side of it. So we have given the wave functions psi c and psi v. We can substitute these wave functions over here and we can solve this integral given in equation number 8. The integral in equation number 8 can be split into two integrals, one over the transverse coordinates x and y, and the other over the longitudinal coordinate z. So we are now substituting these wave functions into equation number 8, and the simplified integral is given. So the absolute square of h12 prime is equal to 2, we have, as I said, we have divided the integral into two parts. One is the absolute square of the terms that we have included, and the other is the absolute square of the terms containing sine functions. Because here we shall integrate it with respect to dz, and in the above we shall integrate with respect to dx and dy. You see that I have omitted the integral sign over here due to the shortage of space. But you see that there is a sign of integral over here. So remember that the sign of integral is present on the left of each. And since the variables dx and dy are separable, so we can separate out the two integrals. That is, there is one integral sign on the left hand side, that is on the left hand side, and there is another integral with the terms containing sine functions. So these are the two integrals. So one integral will have dx and dy, the other integrals will have dz over there. So the integral will vanish unless the integral will be non-zero if this condition is satisfied. That is, KC perpendicular in vectorial form is equal to KV perpendicular in vectorial form plus KW in the vectorial form, where KW is the wave number associated with the incident wave. This is because why the integral will vanish if this condition is not satisfied. It is because KVW, the mod value, that is the absolute value of KVW, is much less than KC perpendicular, and also KW is much less than KV perpendicular. Thus we write KC perpendicular is equal to KV perpendicular. Such a condition has also been discussed in one of the previous slides, and we have declared it as K selection rule. So here we have also obtained the same condition over here, that is KC perpendicular is equal to KV perpendicular. That is, the K conservation rule holds for a transition in the transverse direction to the K perpendicular, that is in the vertical direction shown in figure of 72.3. So K conservation rules will be applicable in the direction perpendicular to the Z direction, that is in the direction of transition, that is in the direction of the in the vertical direction given in the figure 72.3. The integral to be non-vanishing also requires that the positive integers nc and nv must satisfy the condition, that is delta n is equal to nc minus nv equal to 0. You see that we have discussed nc and nv to be integers in equation number number 9 and 10, where we have defined the block wave functions for the conduction band and for the valence band. And here we have defined nc and nv to be integers. These integers may be referred to as the quantum numbers also. So delta n, that is nc minus nv, that is the change in quantum number, should be equal to 0. That is, what is the meaning of this one? So you see that we have defined one rule given in equation number 10. This rule is required to make this integral, that is to make this integral in equation number 8 to be non-zero, and this is one of the rule. So the integral, when the integral will be non-zero, it means that the transition will be possible. So this is one rule given in equation number 12. The other rule is that delta n is equal to nc minus nv is equal to 0. This condition must be satisfied if the integral is to be non-zero, that is the transition to hold. So that is a stimulated transition occurring from a sub-level in the valence band to a sub-level in the conduction band, and vice versa, must have the same quantum number n. That is, the two states must have the same quantum number. So if you want to move the, for example, if you want to move an electron from the valence band to a conduction band, then both must have the same quantum numbers. For example, if you want to move from n is equal to 1 level to the n is equal to 1 level of the from the valence band with the level n is equal to 1 to the conduction band with the quantum number level n is equal to 1, then of course the delta n will be equal to 0 and the transition will be possible. In the interaction Hamiltonian, there is no dependence on the spin of the transition electrons, which means that the stimulated transition will occur between two sublevels, one in the valence band and the other one in the conduction band with the same spin, that is delta s is equal to 0. That is the change in the spin, that is delta s is equal to s1 minus s2 equal to 0. That is the change in spin will be equal to 0. That is the electron in both spins in both states must have the same spin. So you see that these are the three rules that are required for the transition, for the stimulated transition to hold, either stimulated absorption or stimulated emission. And the rules are listed in equation number 12, in equation number 13 and in equation number 14. The three transition rules will hold even when the incident wave E of R is not confined or polarized on the quantum well plane, as we have imposed this restriction earlier, but this restriction was imposed for the sake of simplicity in calculations. But you know that later we can find out with the detailed analysis that this condition is not necessary. That is, E of R is not required to be confined or to be polarized in the quantum well plane. So all these queries asked in the questions have been answered. So this is the end of slide number 73.